Can you see my slide now? Chapter 6 on solutions and colloids. Can you see the slides page now?
Yes.
All right. Last chapter, we went over gases, liquids, and solids. Most of it is on gases. So in this chapter, we're going to look at solutions and colloids. Let me explain how we came to this point. Remember in chapter 1, we talked about states of matter. Then in chapter 5, we go on over details of states of matter, gases, liquids, and solids. Also in chapter 1, we started classification of matter as homogeneous and heterogeneous mixtures. The matter is present mostly in complex mixtures, mixture of more than one compound, element with another different element, or element and a compound. They are found as mixtures. So this chapter is about mixtures. This is the expansion of homogeneous mixtures. There are two types of mixtures. We're going to introduce two types of mixtures. One is homogeneous. Composition is uniform throughout the sample. Heterogeneous, composition is different. In this chapter, we mainly focus on homogeneous mixtures. Heterogeneous mixtures are too complex. We cannot predict uniform properties for them. Therefore, we don't deal with heterogeneous mixtures. A solution is a homogeneous mixture, as well as colloid. Colloid is a homogeneous mixture too. There's a difference between a real solution. We're going to talk about real homogeneous solutions. Colloid is not a real homogeneous solution, homogeneous mixture. It has particle sizes of one of the component is larger. Normally the particle size in homogeneous mixtures, which are mixed up uniformly, are about 1 nanometers. Colloids have greater than 1, about 1 nanometer, 10 nanometer. We're going to talk about in 6.7, section 6.7, chapter 7, 7th section about colloids. We will wait till then to discuss about particle sizes, how they make colloids different from most of the homogeneous mixtures, which are solution. So we're going to talk about most of the common types of homogeneous mixtures, which are solutions. Solution is a name for another name for homogeneous mixture. There are some characteristics for homogeneous or mixtures or solution. We're going to discuss about them. Also, when you produce a mixture, how they mix to produce a homogeneous solution, homogeneous mixture, is based on solubility. When they mix up thoroughly, that means they're soluble. If they're not mixing up homogeneous mixtures, two components doesn't mix together. They're insoluble. We're going to look into factors that allow two components to go into a homogeneous mixture, two or more components. The most of the common concentration units are discussed in 6.5 section. Concentration is the relative amount of one component in the mixture. We're going to look into this. I'm not going to talk about chapter section 6.6, 6.7, 6.8, and 6.8 right now, because first we go over section 6.1 to 6.5, then discuss later. I will come back and review. I am also not going to go through instructional objectives for chapter 6, because right now there are a lot of details. Once we go over next time, I will come back and review what we done. So did you get the idea that we are expanding the idea about homogeneous mixtures in this chapter, homogeneous mixtures? Homogeneous mixtures are solutions. Commonly, a solution is a liquid, something dissolved in a liquid is called a solid dissolved in a liquid is mostly what you have seen as a solution. We normally call solution, we deal with a lot of solids dissolved in water, aqueous solution, aqueous homogeneous solution. So let's look at how many types of homogeneous mixtures that can be produced by different types of compounds in different phases. A phase is a solid or liquid or gas phase. So let's look at types of homogeneous mixture. Homogeneous mixture has two components. First component is present in large amount, major part of the solution is solvent, and small fraction of other compounds are dissolved. So small amount of compound that dissolve in a solvent is called solute. Solute is a substance that dissolves in a solvent to produce a solution in small amounts. Major component is the solvent. Therefore, homogeneous mixture, which you call solution, normally has two components, solvent and the solute. Let's see how we mix up different phases, compounds in different phases to produce homogeneous mixtures. Let's look at solute, solvent, and how they appear, and examples. Gas, some compounds are present in gas phase, carbon dioxide, methane, or nitrogen elements. When a gas goes into a gas, mix up gas together, they also form a homogeneous solution, homogeneous mixture. We normally don't call it a solution, but it is a gas solution. For example, air is a homogeneous mixture of mainly nitrogen and oxygen. Example is air. Gas in a liquid. Now, carbon dioxide can be dissolved in water to produce carbonated water. The major components is solvent is liquid, which is water, in carbonated water. The other small amounts of gas is dissolved in water. Therefore, this is how we produce homogeneous mixtures with different gas or liquid or solid phase combination. Gas in a solid is also a homogeneous mixture. A cloud is an example of gas gone into solid solvent. Solid is a major component. The cloud is whitish. Therefore, it is different from regular solutions. Liquid in a liquid is very common. Wine is an example of liquid in a liquid. Wine has alcohol and water. Water is the solvent in wine. Alcohol is the solute, which is present in small amount. Wine also has other ingredients like coloring material coming from the fruit we use to produce wine. Wine has red color because red wine is made from red grapes. White wine has white color because it was produced from white grapes. So it's not a totally simple solvent solute, but there are other components in wine. But they are all homogeneous, mixed up uniformly. Solid in a liquid is very common type of homogeneous mixtures. They're called, normally we call solid going into a liquid as a solution. For example, if you put salt in water, you got salty water or salt water solution, aqueous solution. The solute is the sodium chloride, which is present in small amount. Solvent is the water. So this is common example. Then the last one, solid also can produce homogeneous mixtures. They mainly, if you look at all these combinations, solvent, the form of the solvent, whether it's a gas, liquid, solid, take up the appearance of the solution. Major component, solvent, form the appear. In a gaseous mixture, where solvent is a gas form. When gas goes into liquid, solvent is a liquid appearance. Gas in a solid is a solvent solid appearance. Liquid in a liquid, again, liquid appearance. Solid in a liquid is a major component, solvent, therefore liquid appearance. In a solid homogeneous mixture, examples are metallic mixtures like alloys. Alloy is a mixture of two metals, copper and zinc, together forms alloy called brass. Alloy is metallic mixtures. Brass is a very common solid homogeneous mixture. So how many of you got the idea now? Solutions are very broad, have a solution, a meaning of a solution is very broad. It's not just a liquidy solution. It could be homogeneous mixtures of different states of matter. compound mixture of compound in different states mix up to produce different appearances. Now let's look at what are the characteristics of homogeneous mixtures. Now I am talking about solutions. I mean homogeneous mixtures. What are the characteristics? Let's look at it. As we discussed, homogeneous mixtures, distribution of components in the solution is uniform. In a sodium chloride solution, sodium is present uniformly with water in every part of the solution, homogeneous mixture. Now, another characteristic of any homogeneous mixtures we listed in the previous slide. The components don't separate on standing. If you leave them alone, they stay as they are. So that is one thing. They don't settle down. They don't separate. A solution cannot be separated into components by filtration. If you have a sodium chloride solution or any other homogeneous mixture, a filtration cannot separate components because they are smaller than holes in the filter paper. So they all pass through. For any given solute-solvent combination, we discuss about gases, liquids combination. It is possible to make solution of many different compositions. The composition of homogeneous mixture is not fixed. You can mix different amount of solvent material with solute to make many different ratios of compositions. The fifth characteristic is solutions are almost always transparent. You can see through a sodium chloride solution. Any chemical compound that dissolves in water is transparent. Now, I need to bring this up here. The difference between solution, homogeneous mixture, and a colloid, which is also a homogeneous mixture. There are real solution, homogeneous mixtures, which are transparent, but the colloids are opaque. For example, sodium chloride dissolved in water is a transparent solution. Milk is different proteins dissolved in water. Milk is produced by the lactate from the breast of a cow, which contain a lot of proteins, some sugars, complex mixture, but milk is a colloid. It's not transparent. Colloids are cloudy. Milk, you cannot see through milk. Therefore, milk is different from solution. That's why we discuss milk as a colloid. We're going to talk about that. Really, except colloids, all other solutions are transparent. Solution can be separated into pure compounds. Solutions are just mixing solvent and solute, there's no chemical change between chemical reaction between solvent and the solute. Therefore, there are separation techniques that could separate two components of the solvent-solute components from the homogeneous mixture. For example, if you have water-alcohol mixture, you can distill the alcohol out and separate alcohol and the water. Also, chromatography. If you have color material, different colors in a mixture, colored material, depending on their movement along the chromatographic paper, you can separate chlorophyll into its component. Chlorophyll contains a lot of components in water. When you dissolve chlorophyll, extract chlorophyll into water, you can separate the chlorophyll from carotenes, which are yellow colored. Therefore, distillation or chromatography can be used to separate the pure components of a homogeneous mixture. Now, how a solution is formed is based on the idea. If the solute goes into solvent, we call it solute is soluble. Solubility is common word we used previously. Ionic compound going into water, we call it soluble. So this is the same idea. We talk about solubility. What factors affect the solubility of a solute in a solvent? Solubility is defined as the maximum amount of solute that dissolves in a given amount of solvent at a given temperature. There's a limit for each solute, how much solute could be put in a particular solvent. For two different solutes, the amount that goes into solvent is different, therefore different solubilities at given temperature. Solubility is a physical constant. You normally give as how many grams of solute are dissolved in 100 grams of solvent. Each solute has a different solubility in every liquid. If you have a solid, it could be soluble in water, but it may not be soluble in alcohol or other solvent. Other solvents are like benzene, organic solvents, alcohol, etc. Those with low solubility are said to be insoluble. We just talked about it. With higher solubilities are called soluble. Some liquids are insoluble in each other. For example, gasoline mixed with water, they separate out into two layers. They are insoluble. They don't form homogeneous solution. Their solubility is very small. Other liquids have limited solubility. In small amount, ether is an organic compound that goes into water, about 6 grams per 100 grams of water. It's limited. If you add more ether into the solution, it separates out. So some solutes goes into the solution in limited quantity. Some are miscible in any proportion. Still, other liquids are completely soluble in each other. For example, alcohol and water, ethanol, the drinking alcohol, and water never separate out, mix in any proportion. They are completely miscible or soluble. Now we are going to look into details of solubility. Based on the solubility characteristics, the homogeneous solutions are three types. First is the saturated solution. Solution in which solvent contains the maximum amount of solute that can be dissolved at the equilibrium at a given temperature. We talked about solubility depend on temperature. So at a given temperature, there's a limit that for each solute that can be put on, especially solid solute like sodium chloride, sugar. After you put maximum amount, rest precipitate out. That's called a saturated solution at a given temperature. Unsaturated solution is that has less than saturated amount. The more solute can be dissolved into the solvent at a given temperature. Unsaturated means it's all less than what it can. Supersaturated solutions are solutions that contain more than equilibrium amount. Here's what happened. If you started putting a solid into a solution and increase the temperature, as the temperature increase, solubility increase. When you cool down the solution after saturated solution are produced at higher temperature, as the temperature is going down, the solute doesn't come out because higher the temperature, higher the solute amount. So there's a situation when you cool down, a supersaturated solution is formed. This is not a stable situation. What happens is when supersaturated solution is disturbed in any way, sometimes small dust particles or adding small amount of crystals of a solute, solubility equilibrium is restored. That means excess solute precipitate out, leaving a supersaturated solution to become a saturated solution with excess solute as solid. So supersaturation, saturated solution, unsaturated, saturated, you should know the idea behind them. Now what really affects the solubility, which means mixing up of a solute in a solvent, what factors affect? Now, one of the most important factors is their chemical nature, their nature. Out of these several factors, nature of the solvent and solute. The more similar two compounds are, that means solvent and the solutes, more likely it is that one is soluble in the other. For example, similarities means mainly they have polar, non-polar nature. Non-polar means they don't have dipoles. Polar means they have dipoles. ions have charge. So non-polar means they have no charge separation. Therefore, polar and ionic compounds are similar. Non-polar compounds are similar in a way they have only hydrogen London dispersion forces, non-polar compounds. We talked about in previous chapter. So like dissolves like comes from this idea. For example, benzene is a hydrocarbon, which is non-polar. Carbon tetrachloride is a non-polar molecule. Therefore, they only has London dispersion. Non-polar are like, or they have London dispersion forces only. Therefore, they mix up. They are soluble together. On the other hand, sodium chloride, which are ionic charged ions, water also have charge separations. Therefore, sodium chloride goes into water easily. Therefore, sodium chloride and water are like substances, like dissolves like. Table sugar, which is sucrose, has a lot of OH groups, like in OH in water. They both can hydrogen bond to each other. Therefore, they are, of course, table sugar, is soluble in water because hydrogen bonding can take place between water molecules and sucrose OH groups. One other, apart from the nature of the solute solvent, temperature also affects. Once a solution is formed, normally for solids, the solubility increase with temperature. You can put more sodium chloride if you heat the solution, or more sugar. There are a few exceptions where the solubility decrease, but mostly solutes increase solubility as the temperature increases. But there's an exception for temperature. For gases to go into a liquid, the temperature decreases the solubility. So temperature, as the temperature increases, solubility decreases. This is an example when you have a carbonated drink. If you warm it up, it goes flat quick. If you keep it with ice in the carbonated drink, it stays longer because as the temperature goes down with ice, solubility increase. If the ice is not put into carbonated water drink, so it goes flat faster. That solubility decreases as the temperature increases. The effect of pressure we talked about temperature. Normally solids increase solubility with temperature, but the gases decrease solubility with temperature. How about the pressure? Pressure don't have only take an effect on one of the solutes. Solute is gas. If the solute is solid or liquid, there's no effect of pressure. We talked about in previous chapter. Liquid and solid do not compress. They are incompressible. They have no effect on volume on the pressure. But the pressure has effect on gases only. Pressure has little effect on the solubility of liquid or solid in each other. The solubility of a gas increases. Gas increases as the pressure increases for the gas or the solution. For example, solubility of carbon dioxide in carbonate beverages increase that's how you produce carbonated drinks, carbonated water. Put the carbon dioxide on top of the liquid and increase the pressure. Then the carbon dioxide goes into the water, producing carbonated water. So we gone through basic introduction to homogeneous mixtures. Now we are trying to explain how we define relative amounts of, we talked about solubility, but we want a more precise composition, how you show the composition of solution. Concentration of the solution is based on relative amount of solute are found in the solution. First, we use percent composition. For example, percent composition is 1/1 part per 100 is 1 part per 100. Let me write that. Normally 1 divided by 100 is percent. 1%. If you have 100 parts per 100, is 100%. Weight percent is one of the percentage concentrations we use, weight by weight. Sometimes we write mass by mass. I will go with WW, which means on the top is weight of the solute. We are only talking about two component mixtures right now. The bottom W is total solution, weight of the total solution. Essentially, the weight of the solute to the weight of the solution expressed as a percentage. So that means you get the weight multiplied by weight divided by weight multiplied by 100. You get the weight by weight percentage. Sometimes we use volume percentages, weight by weight. In place of weight by weight, we use weight by volume by volume. Why we use volume by volume? When we measure solute volume and the total solution volume, this is more appropriate when our measurements are made in volume. In the previous one, measurements are made in mass or weight. Here the measurements percentage is given for volume measurements. So for example, if you take 40 milliliters of ethanol and make up a solution, total volume of the solution is 100 millimeters. Therefore, percentage is multiplied by 100 is 40%. So that's how you get calculate the percent weight by volume comparison. Sometimes for solid liquid solutions, solid is measured in weight. Volume of the solution is measured in volume. So this example, 10 grams of table sugar in 100 grams of total solution is 10% solution. Now, this is the percent composition of solute to solvent, one component in the solvent. So this is simple calculation. We also use moles per liter. In chemistry, the mass could be converted to moles. We already gone over it. Mass divided by molar mass, you get the number of mass divided by molar mass, you get number of moles. Therefore, we normally weight or mass is converted to moles. This is like a weight by volume ratio. It's not the percentage. This is moles per liter. This moles per liter concentration is called molarity. Molarity is a common way to express how many moles of solute are present in the given solvent or given liter of solution. So if you know the moles of solute, liters of solution, it's easy to calculate moles. Molarity is expressed in big M divided by liters of solution gives the molarity. So this is what I was talking about. Molarity is moles of solute, which is moles are written as N liters of solution. That's a fraction. This is not the percent. On previous concentration unit, we use percentages. Example, describe how to prepare 2 liters of 1.5 meter molar. This big means molar. Molarity we call molar, M-O-L-A-R, molar. 0.015 molar sodium hydroxide solution. How do you prepare? Normally you could do it 2 ways. Molarity is moles divided by liters. You can plug in, solve for number of moles. Moles is molarity times liters. So when you do it like a fractal method, you start with molarity. Then you cancel out the liters. So in this case, you get the same answer. 0.15 times 2.0. Answer is 3.0. You can do either plug in the equation molarity is big M is equal to moles divided by liters, or do a factor label method. Convert the definition of molarity into moles. How do you get moles from molarity? Molarity times liters is moles. Molarity times liters. That's the same idea. So you can calculate number of moles or number of how many liters are the solution if you mix up certain number of moles and certain number of solution. Next, convert 0.3 to sodium hydroxide. This is sodium hydroxide. How do you convert moles to grams? You already know. Moles times molar mass is grams. That's the moles. That's the molar mass. 40 is the molar mass of sodium hydroxide. So you get, how do you make up a 0.15 molar sodium hydroxide solution? You take 12.0 grams of water, sodium hydroxide, and add 2 liters to make the solution, total solution, 2 liters. That's how we make a 0.15 molar sodium hydroxide solution. To prepare a solution, dissolve 12.0 grams of sodium hydroxide, enough water to make 2.4 liter solution. So this is how different solutions are, different solution with concentration, molar concentration or certain molarity is produced. We give you a few more examples about molarity. If the concentration of sodium chloride in blood serum is approximately molarity, we call it 0.14 molar. What volume of serum contains 2 grams of sodium chloride? How do you do this? Concentration is given. Grams is given. Volume is of the solution. Volume of the blood serum. They're asking how many liters the serum is. So in this case, you have to convert first grams to moles. How do you do that? Find the number of moles in 2 grams of sodium chloride. You calculate the molar mass of sodium chloride. Add sodium plus chlorine. I think sodium is 23, 35, 58. 58 is the molar mass. You start with grams divided by molar mass. Grams divided by molar mass is number of moles. That's how many number of moles are. Now you have the molarity. So molarity is 0.14, then convert molarity to liters. Or you can do molarity is equal to moles times liters. Therefore, liters is moles divided by molarity. Therefore, the next conversion factor, moles divided by molarity. That's the molarity. 1 over is divided by. So you get the serum solution have 0.24 liters or 240 milliliters. That's how you answer the question. So there are going to be questions little similar to that, so that you should be able to do. These are basic calculation we go over previous chapters. Converting grams to moles, moles to grams are introduced. Now let's talk about another problem. in solution. In the lab, normally what you would do is you have a stock solution. Stock solution is the concentrated solution which we keep in the lab and produce different concentration from the higher concentration, adding water. That's called dilution. Dilution is when you add water to a higher concentrated solution. Molarity is one is greater after you produce diluted, molarity is lower. When you add water to a highly concentrated concentration is molarity is greater than before adding the water, you get molarity lower than the lower molarity after adding the water. Let me describe it again. If we dilute a solution, number of moles of solute remain the same after the dilution. This relation results in the following relationship. This is the one very important. You start with the stock solution, initial solution, and took up add certain volume of that solution and prepare a solution. Now add more. V1 is greater than V2. So there you come up with a new molarity. When you add water to produce V2, second volume, then the molarity change, because molarity times volume is a constant. So this is used in dilution problems. For example, let me talk about an example. How do you prepare this is the final of aqueous solution from stock solution, highly concentration. How do you prepare 200 milliliters? You have to understand this is V2, this is M2. Why? These are final aqueous solution. This is M1, initial, or what you started. They're asking, how do you prepare? So you have to say, you take up, you plug in the values, 6.0 times V1 is equal to 3.5 times 200. Therefore, V1 is equal to 3.5 times 200 divided by 6.0. What do you mean by you take the stock solution, find the volume, V1 is this. You take the stock solution, 0.12 liters, and add, this is 120 liters. 120. How do I get 120? Liter has 1000 milliliters. When you multiply 0.12, 1, 2, 3, 1, 2, 3, yeah, 120 liters. So, I'm sorry, 120 milliliters. You take a 120 milliliter sample of stock solution, add water until it is 200 milliliters, you get the required solution. To prepare a desired solution, place 120 milliliters of stock solution in a 200 millimeter volumetric flask. Fill the flask up to the mark with the distilled water. So this is more precise. You take a flask with 200. You want to make 200. Then you put the 120 in there, add water to it. Then you produce the solution, 200 milliliters of 3.5. So that's how you produce solutions from different higher concentrated solution, stock solution. Concentration is also expressed in parts per billion and parts per million and parts per billion. This is related to percentage. Percentage is parts per 100. This is multiplied by 100. Percentage is divided by 100. This is 10 to the 9. Billion is 10 to the 9. Million is 10 to the 6 divided by 10 to the 6. So sometimes when you have concentration in very small amounts of the solute, you use ppm or ppb. For very dilute solutions, concentration is expressed in parts per million, parts per billion, rather than parts per 100, which is 1 over 10 to the 2. 100 is 10 to the 2. So parts per million is taken in either one of the previously discussed percentage ratio multiplied by percentages, you get the percentage. WW multiplied by 10 to the 6 get the ppm. WW or W divided by V or V over V could be replaced. So units in each reported must be in the same. Maybe whichever quantities are used, the units in each is reported must be same. For example, if you dissolve 1 milligram of lead in 1 grams of water, 1 kilograms of water, that means 1 milligram, you have to convert this to milligram here, must be same. You cannot have different units. So that means 1 milligram in 10 to the 9 milligram, that is ppm. So that is how you get the ppm here. When you convert it, must be in the same units. You cannot have 1 milligram here, 1 milligram here. Weight by weight both should be same. So you can apply this to parts per billion also. So it is when the amount of solute is very low, we use this. I'm going to stop at this point Right now, 2:33. Are you guys there? Are you guys there?
Yes, yes.